The night sky is filled with countless stars, galaxies, planets, and an overwhelming abundance of mysterious objects, among them asteroids. The word asteroid literally means star-like, and it's no coincidence. Even when observed through the most powerful telescopes, they appear as tiny points of light, almost indistinguishable from the distant stars behind them. But don't let their humble appearance fool you. These cosmic boulders have played a pivotal role in the birth of our solar system, and ultimately, the formation of Earth itself. From small rocks the size of a car to gigantic chunks hundreds of miles wide, asteroids are far more than just space debris. They are time capsules, ancient remnants from the formation of our planetary neighborhood, offering a glimpse into how everything, including life as we know it, came to be. Scientists estimate there are trillions of them scattered across the solar system, especially concentrated in the asteroid belt between Mars and Jupiter. This vast collection of rock and metal is a treasure trove of cosmic history. Roughly 4.5 billion years ago, our solar system was just a swirling cloud of gas and dust, forming a massive rotating disk around the infant sun. As gravity pulled particles together, clumps began to form, some of them evolving into asteroids. These early building blocks collided, fused, and created even larger bodies. Over time, some became the planets, while others remained as they were, raw fragments of that ancient construction process. These asteroids, the solar system's original architects, were instrumental in creating Earth. Through a process of relentless collision and accretion, they helped gather mass to form our planet's core. Their constant bombardment added essential elements, carbon, water, and metals, vital ingredients for life. The solar system, in its infancy, resembled a chaotic pinball machine. Trillions of rocky objects swirled around the sun, colliding, exploding, and reshaped the environment. This was a time before the planets had even formed. Asteroids, diverse in size, shape, and composition, were in constant motion, creating a cosmic maelstrom of activity. Some of these rocks were pulled together by gravity to form the terrestrial planets, Mercury, Venus, Earth, and Mars. Others were ejected into distant orbits or captured by larger bodies like Jupiter and Saturn. A significant number, however, remained as asteroids, frozen in time, preserving the story of their origins. It's important to note that asteroids aren't just relics. They're still active participants in the solar system's dynamic evolution. Their gravitational interactions, their collisions with each other and with planets, continue to influence the architecture of our cosmic neighborhood. In fact, some scientists believe that without the chaotic influence of asteroids, Earth may never have formed in the way it did. In the last few decades, missions like NASA's OSIRIS-REx and Japan's Hayabusa 2 have traveled millions of kilometers to collect samples from these distant wanderers. These missions aim to answer fundamental questions. What are asteroids made of? How old are they? And what can they tell us about the early solar system? Interestingly, despite their rocky makeup, some asteroids are surprisingly rich in water and organic compounds. This discovery has led many scientists to theorize that asteroids may have played a critical role in delivering the building blocks of life to Earth. Long before the first oceans formed, icy asteroids may have rained down on our young planet, carrying with them the ingredients for biology. Asteroids also remind us of our vulnerability. Their paths are unpredictable, and a single strike could have catastrophic consequences for life on Earth. History shows us how impactful these celestial bodies can be, the most famous example being the Chicxulub impact, which likely caused the extinction of the dinosaurs 66 million years ago. But even in destruction, asteroids have reshaped life. Without that mass extinction event, mammals, and eventually humans, might never have emerged. In a very real sense, we owe our existence not just to the creation of asteroids, but also to their violent collisions. Today, Space agencies around the world are monitoring thousands of near-Earth asteroids, cataloging their trajectories, and developing planetary defense strategies. Projects like NASA's DART mission, which successfully altered the path of an asteroid in 2022, demonstrate our growing ability to protect Earth from future impacts. Asteroids, once mysterious and overlooked, are now at the center of space exploration and planetary science. They are more than cosmic leftovers. They are teachers, time travelers, and perhaps even lifesavers. As we continue to explore these rocky bodies, each new discovery brings us closer to understanding our own origins. The story of Earth, the story of life, and the story of the solar system are deeply intertwined with the story of asteroids. And this journey into the cosmos is only just beginning. Stay with Infinity Beyond as we uncover the secrets of the universe, one asteroid at a time.
In our own solar system, and in every solar system discovered so far, the first large objects to form are asteroids. Long before the birth of planets, these rocky fragments were already spinning around their young stars. There were no stable orbits yet, no well-formed worlds, only chaos. Trillions of rocks and stones churned within the swirling disks of dust, orbiting in what can only be described as cosmic turbulence. Imagine a vast merry-go-round of space debris encircling the sun, where collisions were inevitable and frequent. Some of these rocks clumped together, gaining mass with each impact, slowly growing into the planetesimals that would one day become planets. Others were cast out or destroyed in the relentless gravitational ballet. Yet millions survived, locked in orbit as asteroids, each carrying a unique signature from the early solar system. The asteroid belt, situated between Mars and Jupiter, is the most famous graveyard of these ancient wanderers. But calling it a belt may be misleading. It's not a dense wall of rocks as often portrayed in science fiction. Instead, it's a sprawling region filled with scattered remnants, millions of space rocks, most separated by hundreds of thousands of kilometers. Still, gravitational disturbances from Jupiter's immense mass have prevented these rocks from coalescing into a planet. Each asteroid within the belt is a window into a different chapter of our solar history. Some are made primarily of metal, others of rock, and some contain surprising amounts of water ice. Their diversity speaks to the incredible range of conditions present during the formation of the solar system. Studying them helps scientists reconstruct those ancient environments. What's fascinating is that the paths of asteroids aren't fixed. They're influenced by gravitational tugs from planets, especially Jupiter, and by subtle forces like the Yarkovsky effect, where the way an asteroid absorbs and re-emits sunlight can slowly alter its trajectory over millions of years. This means asteroids can migrate from their original orbits, making their way closer to Earth or out into the deeper solar system. They don't all follow the same direction either. Many move in eccentric, tilted, and unpredictable paths, often crossing the orbits of planets. Sometimes they collide with each other in spectacular fashion, sending fragments flying in all directions. These collisions can create asteroid families, groups of fragments that share a common origin, still traveling in similar orbits, thousands or even millions of years later. While some asteroids remain in the main belt, others have been captured by the gravity of larger planets. Jupiter, in particular, has collected its own group of asteroids called the Trojan asteroids. These objects travel in stable points ahead of and behind the gas giant along its orbit, another cosmic reminder of how gravity sculpts the architecture of space. One especially intriguing class is the near-Earth asteroids. These are the ones that come close to our planet's orbit. Some are harmless, simply passing by at safe distances. Others, however, raise alarms. Even a small asteroid, if it were to impact Earth, could unleash devastation comparable to a nuclear explosion. That's why international observatories and space agencies work tirelessly to catalogue and track these celestial neighbours. Yet, despite the danger they pose, asteroids offer incredible opportunities. For instance, they contain vast resources: iron, nickel, water, and even precious metals like platinum. In the not-so-distant future, asteroid mining could become a reality, unlocking new possibilities for space travel and industry. Water extracted from asteroids could support deep space missions by providing both drinking water and fuel via electrolysis. But returning to their story in the early solar system, it's important to understand the sheer speed at which these objects move. Traveling at tens of thousands of kilometers per hour, their collisions are not gentle bumps. They are violent impacts that melt rock, release massive energy, and reshape surfaces. Over time, these impacts grind asteroids down, leaving many as rubble piles held together loosely by gravity. Some, however, have survived relatively intact, preserving their original structures for billions of years. These pristine relics are like time capsules, and they're prime targets for robotic exploration missions. NASA's Dawn mission visited Vesta and Ceres, two of the largest bodies in the asteroid belt, revealing fascinating geology and possible signs of past water activity. Ceres in particular may even have an internal ocean. Another factor that makes asteroids so interesting is their unpredictability. While their general orbits can be mapped, small forces like solar radiation pressure or gravitational nudges from other objects can alter their paths over time. This makes long-term predictions of their movements a complex and ongoing challenge for astronomers. Beyond the scientific curiosity, asteroids serve as cautionary tales. Earth has been struck before, and it will be again. The Tunguska event in 1908 flattened over 2,000 square kilometers of Siberian forest, likely caused by an asteroid just 50 to 60 meters wide. More recently, in 2013, a 20-meter asteroid exploded in the atmosphere over Chelyabinsk, Russia, injuring over 1,000 people. Yet these events have also spurred innovation. NASA's DART mission, Double Asteroid Redirection Test, successfully altered the orbit of an asteroid in 2022, proving that we can take action against potential threats. It was a small but vital step toward planetary defense, turning science fiction into science fact. Asteroids are not just rocks drifting in space. They are players in a cosmic narrative of creation, destruction, and rebirth. From shaping the planets to potentially ending life, from preserving ancient chemistry to promising future resources, they are among the most dynamic and meaningful objects in the solar system. At Infinity Beyond, our mission is to bring you closer to these forgotten giants of the cosmos, to uncover their secrets, understand their dangers, and celebrate their contributions to the story of everything. Stay tuned as we journey deeper into the asteroid belt, where every rock has a tale and every orbit carries echoes of the past.
Asteroids may seem like simple chunks of space rock, but their legacy on Earth is anything but ordinary. In fact, some of the most pivotal moments in our planet's history were written by these celestial objects, not in ink, but in fire, dust, and extinction. The story begins long before the age of dinosaurs, in a time when Earth was still young and volatile. Back then, the planet endured constant asteroid bombardment. Known as the Late Heavy Bombardment, this period occurred around 4 billion years ago, during which asteroids relentlessly pelted Earth and the Moon. It was a cosmic assault that reshaped the planet's surface and likely sterilized it multiple times. But here's the paradox. Despite this violence, many scientists believe that asteroid impacts may have played a crucial role in bringing life to Earth. Certain asteroids carry not only water ice, but also complex organic molecules, the fundamental ingredients for life. When they struck Earth, they could have delivered amino acids, carbon compounds, and even water, seeding our planet with the raw materials necessary for biology. One particular class of meteorites, called carbonaceous chondrites, has been found to contain amino acids, the building blocks of proteins. These meteorites are fragments of ancient asteroids and provide compelling evidence that the essential components of life may not have originated on Earth at all. Instead, they might have arrived from space. This possibility challenges long-held assumptions about our origins. Were we born solely of Earth's chemistry, or are we the result of cosmic delivery systems? couriers of life riding ancient rocks through the void. Fast forward to about 66 million years ago, and we encounter the most famous asteroid impact in history, the Chicxulub event. This catastrophic collision with a 10-kilometer-wide asteroid triggered a global extinction that wiped out over 75% of life on Earth, including the non-avian dinosaurs. The impact created a crater more than 150 kilometers in diameter and caused wildfires, tsunamis, and an impact winter that plunged the planet into darkness. As devastating as it was, the Chicxulub impact also marked a turning point in evolutionary history. With the dinosaurs gone, mammals began to flourish, eventually leading to the rise of humans. Once again, we see how asteroids are tied not only to destruction, but also to transformation and opportunity. The effects of such impacts can be global and long-lasting. Tiny particles launched into the atmosphere can block sunlight, disrupting climate and ecosystems. But in the grand scheme of things, these events have helped reset the evolutionary clock, forcing life to adapt or perish. Even today, our planet bears the scars of asteroid impacts. From the vast Vredefort crater in South Africa to the Barringer crater in Arizona, Earth's crust is pockmarked with the reminders of these ancient collisions. Some are visible from space, others lie buried beneath sediments, only discovered through advanced imaging and geological studies. It's important to understand that Earth exists in a cosmic shooting gallery. Thousands of near-Earth objects are tracked by astronomers, and new ones are discovered all the time. While most are small and pose no threat, even an object just a few dozen meters wide could cause massive regional destruction if it struck a populated area. This is why space agencies across the globe have stepped up their asteroid defense initiatives. Early detection is key. Projects like NASA's NEO Surveyor, along with international databases, work day and night to map out potential threats. The more we know about these objects, their size, composition, and orbits, the better our chances of diverting them if necessary. One promising technique is kinetic impact. The aforementioned DART mission demonstrated that by crashing a spacecraft into an asteroid, we can slightly alter its course. A small nudge that, over time, can make a big difference. Other proposals include gravity tractors and even laser ablation, where concentrated light slowly pushes an asteroid off track. Beyond protection, there's a new wave of thinking. What if we harness asteroids instead of fearing them? As mentioned in previous segments, asteroids are rich in resources. Mining them could provide metals, minerals, and even water for use in space colonies or long-term missions. Companies and space agencies alike are investing in the future of asteroid mining, with hopes that these space rocks could fuel our journey to Mars and beyond. But this isn't just science fiction. Missions like OSIRIS-REx, which successfully collected samples from the asteroid Bennu, show how much we can learn, and potentially gain, from these ancient travelers. Bennu itself has a 1 in 2,700 chance of impacting Earth in the late 22nd century, making it a particularly interesting subject of study. Learning about asteroids isn't only about curiosity, it's about survival. By understanding their behavior and composition, we are arming ourselves with the knowledge to protect our planet. More than that, we're discovering the very ingredients that make life possible. At Infinity Beyond, we believe that the story of asteroids is deeply intertwined with the story of humanity. From the earliest seeds of life to the existential threats of extinction, asteroids have been there at every turn. They are the destroyers and the deliverers, the harbingers of both doom and destiny. As we look to the future, our relationship with these ancient objects will evolve. What once inspired fear may one day inspire hope. Asteroids could be the stepping stones that help us expand into the cosmos, turning ancient threats into modern-day opportunities. The cosmic dance continues, and we're only just beginning to understand the choreography. Join us in the next chapter as we dive deeper into asteroid missions, planetary defense strategies, and what it means to be a species capable of altering the course of space rocks millions of miles away. For centuries, humanity has looked to the skies for answers. We've asked who we are, where we came from, and whether we're alone. But as we begin to explore space with new eyes and new ambitions, a more practical question emerges. What if the future of civilization lies not on Earth, but in the asteroids? Asteroids, often seen as cosmic threats or ancient relics, are now being reimagined as celestial gold mines, sources of the raw materials that could one day support entire economies beyond Earth. In fact, asteroid mining is no longer science fiction. It's an emerging frontier in both commercial and scientific exploration. Why asteroids? These rocky bodies contain a wide array of valuable elements. Many are rich in metals like nickel, cobalt, iron, and even precious materials such as gold and platinum. Some contain water ice, which can be converted into drinking water or split into hydrogen and oxygen, key ingredients for rocket fuel. Mining Earth's crust is expensive, polluting, and increasingly limited. But the asteroid belt between Mars and Jupiter holds an estimated 700,000 quintillion worth of resources. That's more than enough to elevate every human being to billionaire status, at least on paper. More realistically, asteroid mining could drastically shift how we approach industry, energy, and survival in space. Instead of launching everything from Earth, future missions could rely on off-world resources harvested from asteroids. These rocks could fuel spacecraft, build habitats, and provide life support materials for colonies on the Moon or Mars. But how would it work? First, space agencies and companies must identify the right asteroids, those that are both rich in resources and relatively accessible. Near-Earth asteroids, NEAs, are prime targets. These are asteroids whose orbits bring them close to Earth, reducing the cost and complexity of reaching them. Next comes extraction. One proposed method is robotic mining, where autonomous spacecraft would land on an asteroid, drill into its surface, and extract materials. Another method involves heating the asteroid to release water vapor, which can be collected and stored. In some cases, the entire asteroid might be brought into lunar orbit or Earth orbit for easier processing. While we're still in the early stages, real missions have already paved the way. NASA's OSIRIS-REx collected samples from the asteroid Bennu, giving scientists critical insights into the composition of potentially miniable asteroids. Japan's Hayabusa returned samples from Ryugu. These missions mark a turning point in understanding what's possible. Private companies are also stepping into the game. Firms like Planetary Resources and Deep Space Industries have developed plans for scouting, prospecting, and eventually mining asteroids. While some early ventures have pivoted or stalled, interest in the commercial potential remains high, especially as launch costs decrease and robotic technologies improve. Asteroid mining offers more than just material wealth. It represents a strategic advantage for any nation or company that gets there first. Control over extraterrestrial resources could redefine global power structures in the 21st century, much like oil shaped the geopolitical landscape in the 20th. Of course, there are challenges. The engineering is complex. Spacecraft must operate in microgravity, with unpredictable surface conditions and harsh radiation. Communication delays make real-time remote control difficult, requiring highly autonomous systems. Then there's the legal frontier. Current international treaties like the Outer Space Treaty of 1967 prohibit nations from claiming celestial bodies. But what about private companies? The debate over ownership, regulation, and ethical use of space resources is only beginning. Environmental concerns also extend beyond Earth. While asteroid mining avoids the terrestrial damage of traditional extraction, there are worries about creating new forms of space pollution or altering orbits in ways that could inadvertently create new hazards. Despite these concerns, the momentum is growing. NASA and the European Space Agency are investing in future technologies, including in situ resource utilization, ISRU, which would allow astronauts to extract and use materials from asteroids or planetary surfaces directly, rather than relying on Earth-based supply chains. In the future, we may see mining outposts scattered across the solar system, robotic fleets hopping between asteroids, collecting ore, and delivering it to orbital factories. These factories could process the materials into parts for satellites, spacecraft, or even habitats. Eventually, this could evolve into a self-sustaining space economy, an entire industrial ecosystem operating beyond Earth's gravity well. Some visionaries go even further. They imagine using asteroid materials to construct space elevators, solar power satellites, or massive habitats like those proposed by physicist Gerard K. O'Neill, rotating space colonies that could house thousands, powered by sunlight and built from the resources of the asteroid belt. The dream of becoming a multiplanetary species is deeply tied to how well we can use the materials already available in space. If we can master asteroid mining, we unlock the potential to expand far beyond Earth, sustainably and indefinitely. At Infinity Beyond. We believe this is more than a technological challenge. It's a shift in perspective. Asteroids are no longer just relics or threats. They're keys to our survival, to our prosperity, and perhaps even to our destiny among the stars. In the next episode, we'll explore how upcoming missions and bold new ideas are shaping the next decade of asteroid exploration. Stay with us, because the future is not just written in the stars, it's mined from the rocks between them. In the vast silence of space, asteroids drift alone, untouched, unexplored, and full of secrets. For decades, astronomers viewed them as little more than celestial leftovers. But in recent years, a new era has begun, one defined by daring asteroid missions that push the boundaries of technology and imagination. These missions are more than scientific exercises. They are voyages into the very roots of our solar system. Each rock visited is a time capsule from 4.5 billion years ago, offering clues to the birth of planets, the origin of water, and the chemistry that may have led to life itself. Among the most iconic of these is NASA's OSIRIS-REx. Launched in 2016, it traveled over 200 million miles to rendezvous with the asteroid Bennu, a small, carbon-rich body with a slight chance of impacting Earth in the next 2 centuries. But what made Bennu special wasn't just the risk, it was its composition. Scientists believe Bennu contains unaltered materials from the early solar system, including organic molecules. OSIRIS-REx spent over 2 years orbiting Bennu, mapping its surface, analyzing its topography, and selecting a landing site. Then, in October 2020, it descended and performed a touch-and-go maneuver, briefly making contact and collecting samples. The event marked the first time NASA retrieved asteroid material to bring home, and it was a triumph of precision engineering and international collaboration. The sample, which returned to Earth in 2023, is already offering insights into the molecular building blocks of life and the formation of planets. But Bennu wasn't the first asteroid to be visited. That honor goes to Japan's Hayabusa mission, which in 2005 became the first to return asteroid samples to Earth, albeit in small quantity. Its successor, Hayabusa 2, launched in 2014 and visited Ryugu, a spinning top-shaped asteroid over 300 million kilometers from Earth. Hayabusa 2's mission was nothing short of science fiction. It deployed rovers onto Ryugu's surface, fired a kinetic impactor to expose subsurface material, and collected multiple samples. The spacecraft then made the long return trip to Earth, delivering its cargo in late 2020. What scientists found was remarkable. Ryugu, like Bennu, held hydrated minerals and organic compounds, hinting at the ancient chemistry that may have helped seed Earth's biosphere. These discoveries suggest that carbon-rich asteroids may have played a crucial role in spreading life-forming molecules across the cosmos. More recently, the European Space Agency has joined the exploration race with Hera, a mission that will follow up on NASA's DART experiment. In 2022, DART successfully redirected the orbit of a small asteroid named Osha Dimorphos by crashing into it, our first demonstration of planetary defense. Hera will visit the impact site to study the aftermath and improve our understanding of how we might deflect future threats. These missions are not just technical achievements, they are critical investments in our planetary security. Understanding how asteroids behave, how their surfaces respond to force, and how their orbits can be changed is key to safeguarding Earth from future impacts. But not all missions are about defense or mining. Some seek knowledge for its own sake. SE's planned Comet Interceptor, though aimed at comets, represents a new approach. Waiting in space for an unknown object, like an asteroid or interstellar visitor, to pass nearby. The idea is to study something we've never seen before in its untouched natural state. One of the most exciting upcoming missions is NASA's Lucy, launched in 2021. Instead of targeting a single asteroid, Lucy will visit several Trojan asteroids that share Jupiter's orbit. These objects are thought to be leftovers from the earliest days of the solar system, possibly even older than the planets themselves. Lucy's journey is unprecedented. Over the next decade, it will travel almost 4 billion miles, visiting 8 different asteroids, each with its own story to tell. The mission could reshape our understanding of how the giant planets formed and how their migrations influence the rest of the solar system. The science behind these missions is incredibly complex. Engineers must design spacecraft that can withstand years in deep space, navigate with pinpoint accuracy, and operate autonomously in alien environments. They must land or collect material without anchoring, since most asteroids have almost no gravity. Everything must work the first time. There are no second chances hundreds of millions of kilometers from Earth. Despite the challenges, each mission brings us closer to decoding the mysteries of the universe. Every rock sampled, every orbit mapped, and every molecule studied deepens our understanding of who we are and where we come from. These missions also capture the public's imagination. Watching a spacecraft land on a spinning asteroid, or seeing it blast a crater to expose ancient materials, feels like something pulled from the pages of a sci-fi epic. But this is no longer fiction. It's the real and thrilling frontier of exploration. At An Infinity Beyond, we celebrate these bold endeavors. They represent the best of humanity: curiosity, courage, and cooperation on a planetary scale. As we continue our cosmic journey, we'll keep you updated on every launch, every landing, and every discovery that takes us one step further into the unknown. Because the secrets of the universe are not waiting in distant galaxies, they're riding silently through space, hidden in the rocky hearts of asteroids. It begins with a flicker in a telescope, a tiny speck moving against the stars. At first it seems harmless, but as the data comes in, the numbers change. Trajectory lines shift, possibilities narrow, and suddenly that speck isn't just a rock, it's a threat. Asteroids have impacted Earth before, and they will again. This isn't science fiction, it's cosmic fact. The Earth exists in a dynamic solar system, constantly moving through a shooting gallery of space debris. Every year, new near-Earth objects, NEOs, are discovered, some as small as cars, others the size of stadiums. and a few of them are on paths that bring them dangerously close to our home planet. We've been lucky. In 2013, an undetected asteroid exploded in the skies above Chelyabinsk, Russia. It was only 20 meters across, but it released the energy of over 30 Hiroshima bombs. The shockwave shattered windows and injured over 1,500 people. And yet, this object came from the sunward direction, a blind spot in our detection systems. It was a wake-up call for astronomers, scientists, and governments worldwide. What if the next one is bigger? What if it doesn't miss? Asteroid impacts are not just theoretical, they're woven into Earth's geological history. The Chicxulub impact, which caused the extinction of the dinosaurs 66 million years ago, was triggered by a 10-kilometer asteroid. But even much smaller ones can cause devastation. A 300-meter object could destroy a major city. A 1-kilometer object could trigger global climate effects. And yet, only a fraction of these threats have been identified and tracked. Thousands more remain unknown. That's why planetary defense has become a top priority for space agencies. Organizations like NASA's Planetary Defense Coordination Office and the European Space Agency's NEO Coordination Center are dedicated to monitoring the skies. Their goal: detect potential threats early, before it's too late. New technologies are emerging to help with this effort. NASA's NEO Surveyor mission, launching in the late 2020s, will place an infrared telescope in space specifically to locate hard-to-see asteroids, especially those approaching from the Sun's direction. Ground-based observatories like Pan-STARRS and ATLAS continuously scan the night sky for moving objects. But identifying a threat is just the beginning. What happens if we find an asteroid on a collision course with Earth? That's where deflection strategies come in. The most promising so far is kinetic impact, literally smashing a spacecraft into an asteroid to alter its path. This was the goal of NASA's DART mission in 2022, which successfully altered the orbit of the asteroid, Dimorphos. It was the first time humanity changed the motion of a celestial object. A small step, yet a monumental achievement. Other ideas are more ambitious. The punched-gravity tractor concept involves flying a spacecraft alongside an asteroid, letting its gravitational pull gradually tug the asteroid onto a different path. There's also laser ablation, where concentrated beams of light heat an asteroid's surface, causing material to vaporize and push it off course. Nuclear options have also been considered, especially for large or short-notice threats. But they remain controversial due to political, technical, and ethical challenges. The key to all these strategies? Time. The earlier a threat is detected, the easier it is to divert. That's why early detection is everything. Despite the seriousness of the threat, it's important to maintain perspective. Earth is hit by small asteroids all the time. Most burn up in the atmosphere. The real danger comes from the rarer, larger objects. And while the odds of a major impact in our lifetime are low, the consequences are so high that preparation is essential. The silver lining is that, for the first time in history, humanity is no longer helpless. We have the tools to search, track, and potentially deflect asteroids. It's one of the few natural disasters we may be able to prevent if we take it seriously. But the work is far from done. Thousands of medium-sized NEOs, those between 140 and 300 meters, remain uncharted. These are the most concerning, as they are large enough to cause regional destruction, but small enough to slip through current detection nets. Public awareness is also critical. Events like Asteroid Day, held annually on June 30th, the anniversary of the Tunguska event, aim to educate the public and encourage global cooperation on planetary defense. Because protecting Earth isn't just NASA's job. It's a responsibility we all share. At Infinity Beyond, we believe knowledge is the first line of defense. By understanding the risks, the technology, and the science behind asteroid tracking and deflection, we empower people to support this crucial work. After all, we only have one Earth. Imagine the day we spot a real threat. Imagine the countdown, the calculations, the mission, the tension as a spacecraft races across the void. Then, impact, deflection, success. A moment where humanity saves itself, not with panic but with preparation. This isn't just a dream, it's a mission in progress. Stay with us on An Infinity Beyond as we explore how science, space technology, and global collaboration are rewriting the rules of survival in the face of the asteroid threat. Because the sky is watching, and now so are we. Between the orbits of Mars and Jupiter lies one of the most intriguing and misunderstood regions of our solar system, the one asteroid belt. Far from being an impenetrable wall of chaos, as often portrayed in science fiction, this vast expanse is a lonely graveyard, a cosmic reminder of what might have been. The asteroid belt contains millions of rocky bodies, ranging from pebbles to dwarf planets. At its heart are ancient objects like Ceres, the largest asteroid and officially classified as a dwarf planet, and Vesta, a uniquely differentiated body with signs of volcanic activity in its past. These objects are more than space rocks. They're fossils from the solar system's violent youth. But here's the mystery. Why didn't all this material become another planet? To answer that, we need to go back to the birth of the solar system. Around 4.5 billion years ago, a swirling disk of dust and gas surrounded the newborn sun. Through a process of accretion, particles began sticking together, forming planetesimals. Many of these merged to become planets: Mercury, Venus, Earth, and Mars. Yet in the region between Mars and Jupiter, something stopped that process. That something was Jupiter. As the largest planet in the solar system, Jupiter's immense gravity disrupted the delicate dance of planet formation. Its powerful pull stirred the region, preventing the building blocks in the belt from coalescing into a single body. Instead of forming a planet, the region remained a scattering of fragments, caught forever in orbit but never united. Over time, collisions between these fragments created the asteroids we see today. Some are solid rock, others are loose rubble piles held together by weak gravity. Their diversity is staggering: metallic, carbon-rich, icy, volcanic, and each type tells a different story about the solar system's evolution. Despite its name, the Gall asteroid belt is mostly empty space. If you stood on an asteroid, chances are you wouldn't see another one nearby. The average distance between large asteroids is hundreds of thousands of kilometers. A spacecraft can pass through the belt without ever encountering a single object. Yet even from afar, the belt exerts profound influence. Some asteroids escape its boundaries, nudged by gravitational interactions or by the subtle but powerful Yarkovsky effect, where thermal radiation slowly alters an asteroid's orbit. Over millions of years, these drifters become near-Earth objects, and sometimes they intersect our planet's path. Other asteroids are pulled into orbital resonances with Jupiter, forming Kirkwood gaps, regions within the belt where asteroids are notably sparse due to these gravitational interactions. These gaps provide insights into the mechanics of orbital dynamics and chaos. The asteroid belt is also a laboratory. Missions like NASA's Dawn, which visited Vesta and Ceres, have provided unprecedented close-up data. On Ceres, scientists found evidence of cryovolcanism, ice volcanoes, and a possible subsurface ocean. This raises questions. Could such a body, once thought inert, support microbial life? Could it have done so in the past? These discoveries blur the lines between what we consider dead space and potentially habitable environments. Geochemically, asteroids in the belt contain elements vital for life and industry. iron, nickel, carbon, and water ice. Future missions may establish mining operations here, especially as humanity pushes toward Mars. The belt could serve as a pit stop or even a resource base for deep space travel. Yet for now, the asteroid belt remains mostly unexplored. We've studied only a fraction of its members, and each mission uncovers more questions than answers. At Infinity Beyond, we see the asteroid belt not as a static field of rocks, but as a dynamic archive of solar system history. These are the failed planets, the would-be worlds that never were. But in their failure, they became something equally valuable. Messengers of deep time. Every cratered surface, every irregular spin, every spectral reading tells us more about how planets form, how they die, and what secrets they carry inside. Some asteroids may be as old as the solar system itself, never melted, never changed, preserving their original chemistry from the dawn of time. Others, like Vesta, show signs of geologic activity, differentiation, and surface evolution, hinting that they came close to becoming something more. In that way, the asteroid belt is not just a graveyard. It's a museum, a puzzle, and perhaps, one day, a gateway. Imagine a future where humanity builds research stations on Ceres, sends rovers from asteroid to asteroid, and harvests resources to power cities on Mars. The asteroid belt could become the backbone of our solar civilization, one stone at a time. So the next time you hear the words asteroid belt, don't think of it as space debris. Think of it as history in motion, silent, scattered, and eternal. Stay with Infinity Beyond as we journey further into this incredible region, where every orbit tells a story and every rock has a memory. Not all asteroids are created equal. While they may look like nothing more than gray, rocky chunks of space debris, each asteroid carries within it a story, written in minerals, metals, and ice. By classifying these space rocks, scientists have decoded vital secrets about the birth and evolution of the solar system. Today we know that asteroids come in several distinct types, each with its own chemical fingerprint, reflectivity, and density. Understanding these types helps astronomers trace where they came from, how they formed, and what role they may still play in shaping the cosmos or threatening Earth. Let's begin with the most common type, the C-type, or carbonaceous asteroids. These make up about 75% of all known asteroids, especially in the outer regions of the asteroid belt. C-types are dark, absorbing most sunlight, which makes them difficult to spot with optical telescopes. What makes them special is their composition. Rich in carbon, water-bearing minerals, and organic compounds, these asteroids may hold the very ingredients that seeded life on Earth. Meteorites that have landed on our planet from C-type asteroids have been found to contain amino acids, the building blocks of life. Missions to asteroids like Bennu and Ryugu have focused on these types for exactly this reason. Next we have the S-type, or silicaceous asteroids, which account for roughly 17% of the population. These are more reflective than C-types and are found mostly in the inner asteroid belt. They're composed of silicate rocks and metals like nickel and iron. Many of the meteorites that land on Earth come from S-type asteroids. S-types are geologically fascinating. Their surfaces can tell us how sunlight, space weathering, and micrometeorite impacts alter rocks in space. These processes mimic those on the surfaces of moons and rocky planets, making S-types perfect laboratories for planetary science. The third major class is the M-type, or metallic asteroids. These are the rarest, comprising just a small fraction of the belt's population, and are primarily composed of nickel and iron. Some scientists believe that M-types are the exposed cores of larger, shattered asteroids that once had molten interiors. Perhaps the most famous of these is 16 Psyche, a massive metallic asteroid located in the middle of the asteroid belt. NASA is currently preparing a mission called Psyche, which will launch a spacecraft to explore this object up close. If successful, it will be the first time humanity has visited a metal world, a place that could be similar to Earth's own core. These three types, C, S, and M, are the primary spectral classifications, but they're not the whole story. With better telescopes and more data, scientists have identified subcategories and hybrids. Some asteroids, for example, have both metallic and carbon-rich regions, suggesting complex formation histories. Others, like D-type asteroids, are extremely dark and reddish, found in the outer reaches of the solar system, possibly rich in organics and ices. Spectroscopy, the science of analyzing the light reflected off an asteroid, is the main tool used to determine type. By studying how different wavelengths are absorbed or reflected, scientists can infer the composition of these bodies from millions of miles away. These differences in asteroid types aren't random. They tell a deeper story about how the early solar system evolved. The inner belt is dominated by rocky and metallic bodies formed close to the Sun, while the outer belt contains more carbon-rich and icy objects that condensed further out. Understanding asteroid types also informs planetary defense strategies. If we ever need to divert an asteroid on a collision course with Earth, its composition and internal structure will determine which technique will work best. A loose rubble pile might absorb an impact, while a solid metal core would respond differently. Asteroid type also affects mining potential. Metallic M-types are rich in valuable materials, while C-types may offer water and volatiles critical for space missions. Some asteroids may even contain rare Earth elements, essential for advanced electronics and energy technologies. And perhaps most fascinating of all, the study of asteroid types expands our view of what is possible in planetary evolution. Imagine a world that never formed because its materials never had the chance. Each asteroid is a fragment of what might have been, a piece of a planet that wasn't. At infinity beyond, we don't just see rocks, we see relics of deep time. Asteroid types are nature's filing system, preserving the records of ancient chemistry, cosmic collisions, and planetary dreams that never came true. So the next time you see an asteroid zip across the sky or hear news of a space mission to one of these mysterious bodies, remember, it's not just a rock. It's a chapter in the solar system's biography, waiting to be read. And we've only begun to turn the pages. Imagine Earth not as the blue and green planet we know today, but as a molten sphere of chaos, a newborn world in a solar system still finding its shape. No oceans, no continents, no life. Just fire, rock, and the relentless bombardment of asteroids. This was our Earth over 4 billion years ago. And the role asteroids played during this time was nothing short of foundational. Long before our planet settled into its familiar form, it was shaped, transformed, and in some ways built by these cosmic invaders. In the early solar system, there were no safe zones. Planetesimals, proto-worlds like Earth, were constantly being pummeled by debris. The solar system was a cosmic battlefield, and asteroids were both the weapons and the architects. During an intense phase known as the Late Heavy Bombardment, LHB, roughly 4 to 3.8 billion years ago, Earth experienced a period of sustained asteroid strikes. These were not just meteor showers, they were global catastrophes. Some impacts were so massive they melted vast regions of Earth's crust. Others delivered something far more valuable: ingredients for life. Asteroids rich in water ice and organic molecules may have brought the building blocks of life to our planet. Carbon-based compounds, amino acids, and even simple sugars, molecules essential for biology, have been found inside meteorites that originated from ancient asteroids. These discoveries support the idea that life's precursors were delivered by cosmic messengers. But asteroids did more than just deliver chemicals. They contributed water itself. In fact, some scientists believe a significant portion of Earth's oceans may have come from asteroid impacts. Measurements of hydrogen isotopes in certain meteorites closely match the water found in our seas. This suggests that at least part of Earth's hydration came from above, not from within. Each impact changed Earth physically and chemically. The crust cracked, molten lava spilled across the surface, and the atmosphere thickened with vaporized rock and gases. But over time, these violent events helped stabilize the planet's structure. Through chaos, order slowly emerged. These early collisions also played a role in forming Earth's core. As metal-rich asteroids smashed into our planet, their iron and nickel may have sunk toward the center, contributing to the dense core we rely on today for magnetic protection and geological activity. Without that core, Earth wouldn't have a magnetic field. And without the magnetic field, life as we know it could never have thrived. The Moon bears the scars of this era, too. Its cratered surface is a permanent record of the bombardment Earth endured. Since Earth's active geology has erased many of its ancient craters, the Moon acts like a cosmic time capsule, preserving the violent history we can no longer see here on our own world. We often think of asteroids only as threats, but in Earth's early history they were so essential creators. They helped form continents, brought life-giving water, and enriched the crust with elements that would become essential for life, like carbon, sulfur, and phosphorus. And the influence of these impacts extended into biological evolution. Even after life began to form, asteroid impacts continued to act as evolutionary filters. The largest ones caused mass extinctions, forcing life to adapt, evolve, or perish. These extinction events reset the evolutionary clock, creating opportunities for new species to rise. The most famous of these came much later, the Chicxulub impact that wiped out the dinosaurs, but it was far from the first. Smaller, earlier impacts may have cleared the path for microbial life, or even selected which molecules survived the planet's volatile infancy. So when we talk about asteroids, we're not just talking about space rocks. We're talking about their origin stories. We're talking about the cosmic chemistry that gave rise to DNA. We're talking about the collisions that cracked open the Earth's crust, forming oceans and continents. We're talking about the ancient delivery of materials that shaped our biosphere. Even now, Earth is still being bombarded, albeit at a slower, safer rate. Each meteorite that lands in Antarctica, each fireball that blazes across the night sky, is a small echo of that ancient age of violence and creation. Missions to asteroids like Bennu, Ryugu, and soon Psyche aren't just about mining or defense. They're about time travel. They let us hold a piece of history in our hands, unchanged for billions of years, and read the story of our planet before there was life, before there was blue sky, before there was us. To infinity beyond. We honor the past not with nostalgia, but with curiosity. By studying asteroids and their role in Earth's early evolution, we're piecing together a puzzle that stretches across time and space. Because Earth wasn't born in peace, it was forged in impact. And within those impacts were the seeds of everything. What if you had 6 months' warning that a massive asteroid was heading toward Earth? It's a scenario once confined to science fiction. But today, it's a serious question being asked in real-world science labs, mission control centers, and government briefings around the globe. Why? Because for the first time in human history, we may actually have the tools to deflect a doomsday rock and save the planet. Asteroid deflection is one of the most fascinating and critical aspects of a planetary defense. Unlike hurricanes or earthquakes, asteroid impacts are the one natural disaster we could theoretically prevent. if we act early enough. Let's break down the leading methods scientists are developing to change an asteroid's path. The most successful and tested so far is the kinetic impactor strategy. This involves crashing a spacecraft into an asteroid at high speed to slightly alter its trajectory. The change is often just a few millimeters per second, but that's enough. Over millions of kilometers, even a tiny shift in velocity can cause a miss instead of a hit. This was exactly the goal of NASA's DART mission, the Double Asteroid Redirection Test. Launched in 2021, DART deliberately collided with Dimorphos, a small moonlet orbiting the larger asteroid Didymos. On impact in 2022, it successfully altered Dimorphos's orbital period by 32 minutes. It was the first time humanity had changed the motion of a celestial body, and it proved asteroid deflection wasn't just possible, it was achievable. But DART was just the beginning. The European Space Agency's Hera mission, set to launch soon, will follow up on the DART impact site to study the crater, the ejecta, and how the asteroid responded to being hit. Together, these two missions form the world's first full-scale planetary defense experiment. Next, there's the gravity tractor concept. This method involves placing a spacecraft near an asteroid and letting their mutual gravity slowly pull the asteroid into a new trajectory. It's a gentle, slow process, but very effective, especially if the asteroid is detected decades in advance. Then there's laser ablation. By focusing high-powered lasers on the asteroid's surface, material is vaporized, creating thrust as gas escapes. Over time, this continuous push can change the asteroid's path. It's a highly precise method, but one that requires significant energy and engineering advancements. More controversial is the nuclear option. In this scenario, a nuclear device is either detonated near the asteroid to deflect it or, in extreme cases, used to fragment it into smaller pieces. While this method delivers immense energy, it raises many questions. What if the asteroid breaks into hazardous fragments? What if the detonation doesn't work as planned? The truth is, no single method is perfect. The right technique depends on the asteroid's size, composition, speed, and, most importantly, how much time we have. Time is the ultimate factor. If an asteroid is detected decades in advance, slow methods like gravity tractors or solar sails could work. But if we only have our months or weeks, faster, more forceful strategies like kinetic impacts or nukes may be our only option. This is why early detection is absolutely vital. Right now, thousands of near-Earth objects, NEOs, have been cataloged, but many more remain unknown, especially smaller ones capable of regional destruction. NASA's NEO Surveyor mission, a space-based infrared telescope, is being designed to improve detection capabilities, especially for hard-to-spot asteroids approaching from the Sun's direction. Ground-based telescopes like Pan-STARRS, Atlas, and others are constantly scanning the sky, tracking known NEOs and discovering new ones. The data they collect feeds into international databases used by scientists and policymakers worldwide. The United Nations has also recognized the importance of planetary defense. The International Asteroid Warning Network, IAWN, and the HUTSA's Space Mission Planning Advisory Group, SMPK, were created to foster international cooperation and decision-making in case of an impending threat. Because in the face of a planetary-scale hazard, no single nation can act alone. But here's the challenge. It's not just about technology. It's also about political will, public awareness, and readiness. If a threatening asteroid were detected today, how quickly could humanity mobilize? Would we act in time? Would countries cooperate or compete? That's why public education, simulations, and awareness days, like International Asteroid Day, are so important. They bridge the gap between space science and everyday life, because the more the public understands the threat and the tools to stop it, the more support planetary defense will receive. At In Infinity Beyond, we believe that preparedness is power. The story of asteroid deflection is not just a tale of rockets and impacts. It's a story of responsibility, of foresight, of choosing not to be victims of the cosmos, but protectors of our only home. The sky is watching, so are we. Let's be ready. In the dark expanse of space, two types of ancient travelers roam: asteroids and comets. At a glance, they seem similar. Small celestial bodies orbiting the sun, relics from the solar system's formation. But the truth is, their differences run deep, and understanding them unlocks secrets about our cosmic origins. Let's begin with the basics. Asteroids are mostly composed of rock and metal. They tend to orbit the sun in relatively circular paths, mostly confined to the asteroid belt between Mars and Jupiter. They formed in the warmer inner solar system, where volatile materials like ice and gas were burned off, leaving behind heavier elements. Comets, on the other hand, are icy bodies composed of frozen gases, dust, and rock. They originate from the high cold, distant regions of the solar system, the Kuiper Belt and Oort cloud. These areas are so far from the sun that water, carbon dioxide, methane, and ammonia all exist in solid form. When a comet approaches the sun, heat causes its ice to sublimate, turning directly from solid to gas. This creates the comet's iconic glowing coma and a trailing tail, which can stretch for millions of kilometers and always points away from the sun due to the solar wind. Asteroids don't have tails. They're dry, airless, and relatively inert. But that doesn't mean they're boring. In fact, asteroids and comets may have once shared common ancestors. Some comets lose their volatiles after many close passes by the sun, becoming darker and more asteroid-like. Conversely, some asteroids have been found to contain small amounts of ice or even exhibit weak outgassing, blurring the line between the two. Take more Comet 67P Churyumov-Gerasimenko, famously visited by the Rosetta spacecraft. This peanut-shaped object is a time capsule of icy material that hasn't changed much in billions of years. Studying its chemistry revealed complex organic molecules, including amino acids, adding evidence to the theory that comets may have helped seed life on early Earth. On the asteroid side, missions like OSIRIS-REx and Hayabusa 2 returned samples from asteroids Bennu and Ryugu, respectively, both containing organic compounds and water-bearing minerals. So while their origins differ, both types of objects have stories to tell about the building blocks of life. Here's another key difference. Orbits. Asteroids generally have shorter, more stable orbits that lie near the ecliptic plane. Comets, especially those from the Oort cloud, can have extremely elongated and inclined orbits, often bringing them into the inner solar system after millennia of isolation. This means that comets can be less predictable and potentially more hazardous if perturbed by gravitational interactions. Their long periods and dimness make them harder to track until they're already racing inward at tens of thousands of kilometers per hour. In terms of threats, both pose risks. The impact energy of either body can be catastrophic. However, because comets move faster and are often larger, their impact potential is even more devastating. Thankfully, such events are rare, but not impossible. One of the best-known impact candidates in history may have involved a comet fragment, the Tunguska event of 1908. Though no crater was ever found, the explosion flattened over 2,000 square kilometers of Siberian forest. Some theories suggest a small comet or icy asteroid disintegrated in the atmosphere, releasing the energy equivalent of a nuclear bomb. So, why does the distinction between asteroids and comets matter? Because it tells us where these objects come from, what they're made of, and how they might evolve. It shapes our strategies for planetary defense, scientific exploration, and even resource utilization. Asteroids may be better candidates for mining due to their stability and proximity. Comets, while harder to reach, offer clues about the outer solar system, solar wind, and even prebiotic chemistry. And then there's the emotional power of a comet, blazing through the night sky, captivating humanity since ancient times. Many cultures saw comets as omens, messengers, or divine signs. Today, we know they are none of those things, but in a way, they are messengers, bringing us news from the furthest reaches of the sun's domain. At Infinity Beyond, we see asteroids and comets not as rivals, but as complementary chapters in the same story. One dry and rocky, the other icy and dramatic, but both crucial to understanding the solar system's formation, evolution, and future. As space missions become more ambitious, we'll explore more of both. NASA's Comet Interceptor, for instance, will wait in deep space for a never-before-seen comet to pass by, ready to study it up close. It may reveal things we've never imagined, because when it comes to these ancient travelers, there's always more than meets the eye. Stay curious, stay watching, and stay with Infinity Beyond. In the vast, empty silence of space, asteroids drift in orbits forged billions of years ago. But what if these relics of the past become the keys to our future? As humanity reaches further into the cosmos, one question looms large. How do we sustain ourselves beyond Earth? The answer may lie in the most unlikely of places: asteroids. These seemingly lifeless rocks are rich with potential. Many contain water, metals, and minerals that could be used for fuel, construction, and life support. Instead of carrying all our resources from Earth, an expensive and logistically complex task, future explorers might simply mine what they need from the asteroids around them. Let's start with one of the most valuable substances in space: water. Water isn't just for drinking. It's a source of hydrogen and oxygen. The two key components of rocket fuel. Through a process called electrolysis, water can be split into its elements and used to power spacecraft. This means that a hydrated asteroid could become a cosmic gas station, a refueling stop in deep space. Asteroids like Bennu, Ryugu, and Ceres have shown signs of hydrated minerals, meaning that water is more common in space than we once thought. Access to in-situ water could dramatically lower the cost of long-term missions to Mars and beyond. Then there's metal, Asteroids, especially M-type metallic asteroids, are loaded with valuable elements: nickel, iron, cobalt, platinum, and even rare earth elements critical for electronics and green energy technology. Instead of mining the Earth's dwindling supplies, future industries could tap into this extraterrestrial treasure chest. Imagine entire spacecraft built in orbit from asteroid metals, or satellites manufactured and launched from platforms in deep space. What once sounded like science fiction is rapidly becoming an engineering roadmap. Mining in space also eliminates many of the environmental concerns plaguing Earth. There's no atmosphere to pollute, no ecosystems to disrupt. And since asteroids are so numerous and small compared to planets, mining them wouldn't drastically alter solar system dynamics. But how do we actually extract these resources? Robotic mining is the most promising approach. Autonomous spacecraft could land on asteroids, drill into the surface, and collect ore, water, or volatiles. Some concepts involve melting ice inside sealed chambers and capturing the resulting vapor. Others propose bagging small asteroids and transporting them to safer orbits like lunar or Earth orbit for easier access. Companies like Planetary Resources and Deep Space Industries have already begun prototyping the technologies needed, even if commercial operations remain years away. NASA and other space agencies are investing in situ resource utilization, ESRU, tech that will allow astronauts to live off the land on future missions. Asteroid resources could support space stations, moon bases, Mars colonies, and even space tourism. Need breathable air? Crack water ice into oxygen. Need radiation shielding? Use regolith from an asteroid's surface. Need structural materials? Refine the metals inside. As launch costs decrease and reusable rockets become standard, the economics of asteroid utilization begin to make sense. Instead of launching every tool, part, and liter of water from Earth's gravity well, future missions could out-assemble, supply, and sustain themselves using space-based resources. But the implications go even further. Some visionaries suggest building space habitats using asteroid materials. Massive rotating stations housing thousands of people, powered by solar energy and shielded by walls of regolith against cosmic radiation. These orbital cities could serve as waypoints between Earth and the outer planets. Others see asteroid mining as a stepping stone to interstellar travel. By learning to harness resources in space, we break free from the limitations of Earth's supply chain. We become a truly spacefaring species. Of course, there are challenges. Microgravity mining is a new frontier. There are questions of legal ownership. Who gets to claim an asteroid? The 1967 Outer Space Treaty prohibits nations from claiming celestial bodies, but private companies operate in a gray zone. There are also concerns about planetary protection. If some asteroids contain prebiotic chemistry, or even life, we must be careful not to contaminate or destroy potential scientific treasures. Still, the potential is too great to ignore. Asteroids could become our lifelines in space, offering everything from fuel and oxygen to metals and water. They could power missions to Mars, build outposts on the Moon, and support a new economy orbiting above Earth. At Infinity Beyond, we see asteroids not as relics, but as opportunities. By understanding them, exploring them, and eventually utilizing them, we open a new chapter in human evolution, one where we live, thrive, and grow beyond the confines of Earth. Because the future isn't just about rockets, it's about resources, and they're already waiting out there, orbiting quietly in the black. All we have to do is reach them. It starts like any other day. Clouds drifting across the sky, birds singing, people going about their lives. And then something changes. A bright light flashes in the upper atmosphere, brighter than the sun. A rumble builds beneath your feet. Seconds later, a deafening roar, followed by a shockwave that shatters glass, topples buildings, and sends people running for cover. This isn't science fiction. It's the real-world scenario that scientists use to model what would happen if a large asteroid struck Earth. But how bad would it be? Could we survive it? At Infinity Beyond, we're diving deep into the science of asteroid impact simulations to understand what such an event would truly look like and how we might prepare. Let's start with the numbers. If a 100-meter wide asteroid, roughly the size of a football field, were to impact Earth, it could release energy equivalent to 130 megatons of TNT. That's over 2,000 times more powerful than the atomic bomb dropped on Hiroshima. An asteroid this size would cause a regional devastation. If it hit land, it could flatten an entire city and start wildfires for hundreds of kilometers. If it landed in the ocean, The impact would generate tsunamis, large enough to flood coastal regions around the world. Now imagine a 500-meter asteroid. That's enough to cause worse continental destruction. The blast would generate intense heat, global shockwaves, and an injection of dust and aerosols into the atmosphere, potentially disrupting the climate for years. And then there's the catastrophic tier. An asteroid is 1 kilometer wide or larger. This is the kind of impact that triggers WASH's mass extinction events. The last time something this size struck Earth was 66 million years ago, when a 10-kilometer asteroid hit the Yucatan Peninsula. The resulting Chicxulub crater was over 150 kilometers wide. The collision vaporized rock, triggered earthquakes, set the atmosphere on fire, and blocked sunlight for months. 3/4 of all life on Earth, including the dinosaurs, disappeared. So how close have we come recently? In 2019, asteroid 2019 OK, a 130-meter rock passed Earth at a distance of just 70,000 kilometers, about 1/5 the distance to the Moon, and we didn't detect it until a day before it passed. That close call sent shockwaves through the scientific community. Since then, detection efforts have improved, but the fact remains, there are still thousands of near-Earth objects, NEOs, that remain untracked. What if we spot one too late? Scientists have modeled hundreds of possible impact scenarios using tools like NASA's Sentry system, ESA's Near-Earth Object Coordination Center, and Purdue University's Impact Earth Simulator. These models consider factors like size, speed, angle, composition, and location of impact. Here's how it might unfold. 1. Detection. Astronomers identify an asteroid on a collision course with Earth. If there's enough time, decades or years, we could attempt a deflection mission, as seen in segment 10. But if the object is only detected weeks or days out, options are limited. 2. Impact location. Ocean impacts might cause tsunamis. Land impacts near cities would result in massive casualties. Even remote impacts could affect the climate and global economy. 3. Blast radius. Depending on size, a shockwave would spread out for hundreds of kilometers. Buildings would collapse. Fires would start. Emergency systems could be overwhelmed. 4. Aftermath. If the asteroid is large enough, it would inject dust into the stratosphere, block sunlight, and drop global temperatures, a scenario known as an impact winter. Crops would fail. Supply chains would collapse. It could take years to recover. So what are we doing about it? Fortunately, space agencies now take planetary defense seriously. Programs like ODART, or NEO Surveyor, and international working groups like IAW and SMPEG are coordinating strategies. But time is everything. The more time we have, the more likely we can stop the impact or prepare for it. Civil defense is also crucial. Cities around the world are starting to build asteroid impact response plans, including evacuation zones, tsunami protocols, and communication strategies. It's not enough to leave this to astronomers. We all must be ready. Because while these scenarios sound terrifying, they also highlight a rare truth. This is one global threat we can actually do something about. At Infinity Beyond, we explore the science not to scare, but to prepare. The universe is not out to get us, but it is unpredictable. The best way to survive a future impact is to understand the threat, respect the risk, and support the science that could save us. After all, the dinosaurs didn't have a space program. We do. Let's make it count. What would happen if astronomers announced tomorrow that an asteroid was heading toward Earth? Would we panic, prepare, or launch a mission to stop it? Fortunately, we don't have to guess. Around the world, scientists, engineers, and disaster planners are running detailed asteroid impact simulations, scenarios designed to help humanity prepare for the ultimate planetary emergency. At Infinity Beyond, we take you inside these simulations to explore how the world would respond, what tools we have, and how close we are to being truly ready. One of the most famous exercises is the WOW Hypothetical Impact Scenario, developed by NASA's Planetary Defense Coordination Office. These simulations are run at global conferences like the HOT Planetary Defense Conference, where international experts are given a fictional asteroid on a collision course with Earth and asked to respond in real time. Each day of the simulation, new information is revealed: the asteroid's size, speed, composition, and potential impact zone. Participants must then decide: do we launch a deflection mission? Do we evacuate cities? What are the legal, political, and ethical consequences? It's not just a game. These simulations reveal how critical it is to have clear communication, international coordination, and public education. They show how every hour counts and how quickly the situation can change. One key lesson: if the warning time is short, less than a year, there may not be enough time to divert the asteroid. Instead, focus shifts to disaster response and home civil protection. Scientists model potential impact zones using tools like Purdue University's Impact Earth Simulator, which calculates crater size, shockwave radius, and thermal radiation zones based on asteroid parameters. NASA's JPL Sentry System, which continuously monitors known near-Earth objects, NEOs, for potential future impacts. ESA's NEO Coordination Center, which works with telescopes across Europe to track and simulate asteroid trajectories. But preparation isn't just about computers and models. It's also about people. Cities and nations need impact response protocols, evacuation plans, emergency communications, backup infrastructure. Hospitals must be prepared for blast-related injuries. Governments must coordinate international aid and logistics. In 2021, FEMA, the Federal Emergency Management Agency, and NASA ran a joint simulation where an asteroid was discovered with only 6 months warning. The result? Not enough time for deflection. The exercise shifted toward assessing which populations could be evacuated, how to disseminate reliable information, and how to prevent panic. One unexpected challenge in these simulations is misinformation. In a real-world impact scenario, social media could spread fear, false claims, or conspiracy theories. That's why scientists emphasize the importance of trusted communication channels. Scientific, transparent, and unified. And what about the tech? If given enough time, 5 to 10 years, missions like DART, Double Asteroid Redirection Test, could be launched to nudge the asteroid off course. Backup options might include multiple kinetic impactors, gravity tractors, or even nuclear deflection. But what if the asteroid is too large? Or if it's a rubble pile, a loosely held cluster of boulders that absorbs impact instead of deflecting? Simulations test all these possibilities. Engineers create 3D models to analyze how different asteroid structures behave under stress. They test how spin, porosity, and shape affect momentum transfer. These models inform how much force is needed and what kind of spacecraft to build. Even student teams now participate in these simulations, designing mission profiles, calculating fuel needs, and presenting ideas at space conferences. The goal is to create a new generation of planetary defenders. Because planetary defense isn't science fiction anymore. In 2022, the DART mission proved we can alter an asteroid's orbit. In the next decade, more missions will test and refine these capabilities. But we're still early in this journey. Simulations also explore post-impact recovery. If we can't stop an asteroid, how do we rebuild? What support systems need to be in place? How do we feed, shelter, and treat survivors? In some simulations, a mid-sized asteroid hits the ocean, creating massive tsunamis. In others, it strikes a remote region, but causes a dust cloud that cools global temperatures and disrupts food production. These scenarios explore how resilient humanity truly is and what infrastructure needs to be strengthened now. Some of the most advanced simulations even incorporate artificial intelligence and machine learning, using real-time data to update predictions and suggest the best mitigation plans dynamically. So where does this leave us? Better prepared than we were 20 years ago, but not invincible. The good news? Scientists, engineers, space agencies, and emergency managers are taking this seriously. Simulations are driving innovation. Policy frameworks are being drafted. Public awareness is growing. At Infinity Beyond, we believe in the power of preparation. Simulations aren't just theoretical. They're dress rehearsals for the real thing. They reveal weaknesses, highlight solutions, and empower humanity with knowledge. Because when it comes to asteroid impacts, doing nothing isn't an option. We may never face a catastrophic impact in our lifetimes, but if we do, the difference between survival and disaster could be the simulations we run today. Stay alert, stay informed, stay beyond. Not all space missions are about exploration. Some are about protection. As Earth orbits through a dynamic and sometimes dangerous solar system, space agencies around the world are stepping up with bold, innovative missions to ensure we're ready when, not if, an asteroid threat arises. And Infinity Beyond. We spotlight the planetary defense missions already underway and those on the horizon that could one day save the world. Let's begin with the most successful mission to date, NASA's DART, the Double Asteroid Redirection Test. Launched in 2021, DART was humanity's first full-scale test of asteroid deflection. Its target? A binary asteroid system called Didymos, specifically its small moonlet, Dimorphos. On September 26, 2022, the spacecraft collided with Dimorphos at over 22,000 km. The result? Dimorphos' orbit was shortened by 32 minutes. A huge success that proved we can change the path of a celestial object using a kinetic impactor. It was the first step in turning science fiction into science fact. But DART was only Phase 1. Enter OES's Hera mission. Set to launch in 2024, Hera will arrive at the Didymos system in 2026 to analyze the aftermath of the DART impact. It will study the crater, map Dimorphos in detail, and measure how the asteroid's structure changed. Together, DART and Hera represent the first planetary defense collaboration between global space agencies. Why is this collaboration important? Because no single country can handle an asteroid threat alone. A global response demands shared data, rapid communication, and trust between nations. That's where missions like Hera and international working groups such as SEMPEG, Space Mission Planning Advisory Group, and IAWN, International Asteroid Warning Network, come into play. But these aren't the only players. NASA is preparing to launch the ANEO Surveyor in the late 2020s, a space-based infrared telescope specifically designed to detect and track asteroids that are hard to see from Earth, especially those approaching from the Sun's direction. With NEO Surveyor, our ability to undetect threats decades in advance will drastically improve. Meanwhile, Japan's Hayabusa 2 mission continues to yield results. After successfully collecting samples from asteroid Ryugu, it returned them to Earth in 2020. Scientists are now analyzing these samples to better understand asteroid composition, structure, and volatility, all essential for building deflection strategies. NASA's OSIRIS-REx mission also made headlines in 2023 when it delivered pristine samples from asteroid Bennu, a near-Earth object with a slim chance of impacting Earth in the next century. Studying Bennu's surface gives us direct insight into how a real-world asteroid might respond to deflection efforts. And then there's Comet Interceptor, an ESA-led mission designed to wait in space for a yet undiscovered comet, or possibly an interstellar object, to pass by. It will provide the first opportunity to study a fresh, unaltered body from beyond the solar system. Every one of these missions builds our toolkit, not just for understanding space, but for defending Earth. But planetary defense isn't just about science. It's also about policy, funding, and public support. The 2021 Planetary Defense Strategy and Action Plan, issued by the White House in the United States, outlines a 5-year roadmap for improving detection, advancing deflection technologies, strengthening emergency preparedness, enhancing international coordination, and increasing public outreach. Similarly, the United Nations Office for Outer Space Affairs, UNOOSA, is working to ensure that planetary defense is globally inclusive, because an asteroid doesn't care about borders. So, what does the future hold? More as simulation exercises between space agencies and emergency services. More dual mission collaborations, like DART and HERA. Development of our fast response interceptors for short-notice threats. Expansion of our space-based detection networks to cover blind spots. And eventually, asteroid deflection tests on larger, more complex bodies. What we're witnessing is the rise of a planetary defense infrastructure, a global shield forged not with weapons, but with science, engineering, and cooperation. And while we hope to never need it, we'll be thankful it exists if we ever do. At Infinity Beyond, we believe these missions are about more than just asteroids. They're about unity, about foresight, about humans taking control of their cosmic fate. For the first time in history, a species on a small planet is preparing to defend itself from deep space. That's not just science, it's legacy, because we are not powerless in the face of the universe. We are learning, we are building, we are ready. And the next time a space rock sets its sights on Earth, it just might meet something we call defense. For centuries, we believed the solar system was a closed world, a family of planets, moons, and rocks orbiting a single star. But everything changed in 2017 when something unexpected hurtled into our view, an object from another star system. It was called Oumuamua, a name meaning scout in Hawaiian, and it marked the first confirmed Sada interstellar asteroid ever detected passing through our solar system. And just like that, the cosmic doors were flung open. At Infinity Beyond, we're exploring what these mysterious Washgor's interstellar visitors are and where they come from and what they might reveal about the galaxies beyond. Let's start with Oumuamua. Discovered by the Pan-STARRS telescope in Hawaii, it entered the solar system on a hyperbolic trajectory, meaning it wasn't bound by our sun's gravity. It was moving too fast, over 87 kilometers per second, and its path showed it had come from somewhere beyond. But that's not what made Oumuamua truly bizarre. Its shape was unlike anything seen before. Based on its light curve, it was estimated to be 10 times longer than it was wide, a flattened cigar or pancake, tumbling end over end. And as it passed the sun, it exhibited ungravitational acceleration, a subtle push that couldn't be explained by gravity alone. It didn't have a visible coma, like a comet. It didn't outgas like typical icy bodies. And it reflected sunlight in strange ways. Was it an icy comet shedding invisible gas? A fragment from an alien world? Or, as some speculated, a piece of alien technology? Most scientists favor natural explanations. Some suggest Oumuamua could be a bent hydrogen iceberg, sublimating invisible hydrogen gas to produce thrust. Others propose it's a push fragment from a shattered planetesimal, ejected during the early stages of planetary formation in another star system. Whatever it was, it raised a powerful question. How many more are out there? Then came the second interstellar object, 2I Borisov, discovered in 2019. Unlike Oumuamua, Borisov looked more familiar. It had a visible coma and tail, like a typical comet, but with a composition unlike anything in our solar system. Borisov contained more carbon monoxide than expected, suggesting it formed in a much colder, more distant region of its home star system. Together, Oumuamua and Borisov proved that two interstellar objects are real, detectable, and maybe even common. We'd simply never seen them before. But now, with advanced sky surveys like Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, coming online, we expect to find many more. These interstellar asteroids are time capsules, fragments of alien solar systems hurled into the galaxy during their formation and now drifting endlessly through interstellar space. Some may carry clues about planetary formation beyond our sun. Others may hold organic molecules, icy compounds, or elements not commonly found in our neighborhood. Incredibly, some scientists propose that these objects could even serve as natural probes, potentially carrying microbial life between star systems, a concept known as panspermia. While speculative, it shows how powerful these visitors could be in shaping life across the cosmos. The next goal? Interception. ESA's Comet Interceptor's mission, launching in the late 2020s, will wait in space, ready to redirect itself toward a yet undiscovered interstellar object. Its goal? Intercept and observe one of these cosmic visitors up close for the first time in human history. Future missions could go even further. Sample return from an interstellar asteroid, giving scientists a laboratory look at materials forged around alien suns. Technologically, these missions are complex. Interstellar objects move fast, approach from random directions, and offer only short windows for observation. But they are also priceless opportunities, windows into solar systems we may never visit. So why does this matter? Because every interstellar asteroid we observe is a messenger from another world. It carries the chemistry, structure, and story of a place we can't reach. A cosmic postcard from far away. These objects also reinforce a powerful truth. The solar system is not isolated. We are part of a dynamic, interconnected galaxy. Rocks from other stars pass through ours and vice versa. In the future, even so our spacecraft, like Voyager and New Horizons, will become interstellar visitors to someone else. At Infinity Beyond, we believe these fleeting travelers remind us of how vast the universe is and how connected everything in it might be. Next time, when you hear news of a strange object passing through the solar system, don't dismiss it. It may have journeyed for millions of years, across light years of space, to reach us, and what secrets it carries might just reshape everything we think we know. For centuries, we feared asteroids as agents of destruction, fiery omens blazing across the sky. But in truth, these ancient rocks are more than just threats. They are storytellers. At Infinity Beyond, we've explored asteroids as builders of worlds, bearers of water, carriers of organic molecules, and time capsules from the dawn of the solar system. But now, in our final segment of this series, we ask the deeper question: what do asteroids teach us about ourselves? Let's start with the obvious: survival. Asteroids show us how fragile life on Earth really is. A single impact has ended entire dynasties of life. Dinosaurs ruled the planet for 160 million years, and a 10-kilometer rock ended that reign in minutes. Had that asteroid arrived a few hours earlier or later, it might have splashed harmlessly into the ocean. Life's path, and ours, would have changed forever. From that perspective, asteroids are cosmic editors, shaping the chapters of evolution, forcing resets, creating new opportunities. But they are also reminders of resilience. Despite extinction events, Earth always recovers. Life finds a way. And now, for the first time in history, one species, ours, has developed the tools to detect, deflect, and prepare for the next big one. That's not just technology. That's transformation. It marks a shift in the role of humanity, from a passive observer of the cosmos to an active participant in our planetary fate. Asteroids also reveal something about our origins. The materials inside carbonaceous chondrites are older than Earth itself, formed in the interstellar cloud that gave birth to the Sun. Studying them is like reading the whole first chapter of a book billions of years long. Some of those rocks carry amino acids, sugars, and water, essential ingredients for life. That means the seeds of life on Earth may have come from the sky. In that way, we are not separate from the stars. We are born of the same cosmic dust that shapes asteroids, comets, and planets. We are stardust that learned to look back at the sky and wonder. Even the act of exploring asteroids is a reflection of our deepest instincts. Why did we send OSIRIS-REx to Bennu? Why did we crash DART into Dimorphos? Why are we building spacecraft to catch objects that come from other star systems? Because we're curious. Because we want to know. Because we care about tomorrow. Asteroids are reminders of how far we've come and how much further we can go. We now understand orbital mechanics well enough to predict asteroid paths decades in advance. We've reached out with robotic arms to touch them. We've flown past them, orbited them, landed on them, and brought pieces of them back to Earth. Each sample, each mission, each pixel of data brings us closer to understanding not just space, but our place in it. There's also a poetic irony here. The same objects that once threatened life are now seen as tools for its expansion. Water-rich asteroids could sustain colonies on Mars. Metal-rich asteroids could build infrastructure in space. They might even serve as stepping stones to other star systems. In short, what was once feared as destruction now promises renewal. But that future depends on choices we make now. Will we fund the missions that detect new threats? Will we share data across borders? Will we educate the public, not just with fear, but with science? Will we teach children that those lights in the sky are not curses, but clues? Asteroids don't just ask scientific questions. They ask moral ones. What kind of species are we? One that waits for impact, or one that acts, one that hoards knowledge, or one that shares, one that only reacts, or one that dares to reach. At Infinity Beyond, we believe asteroids are not just cosmic leftovers. They are cosmic mirrors. They reflect our past, they threaten our present, and they challenge us to build a better future, not just for ourselves, but for every generation after us. Because the next time an asteroid crosses our path, we'll be ready, not just with rockets, but with wisdom. And in that moment, we'll remember, we're not passengers in the universe, we are part of it. Eyes up, hearts open, future forward. This is Infinity Beyond. Far beyond Neptune, at the cold edges of our solar system, something strange is happening. Dwarf planets and distant asteroids aren't orbiting the Sun randomly. Instead, they seem to be clustering, tilting in the same direction, as if nudged by something massive, invisible, and incredibly far away. What could be causing this? At Shushan Infinity Beyond, we explore one of the most intriguing astronomical mysteries of our time, the search for Small Planet 9, a hypothetical giant planet that may be lurking in the outer reaches of our solar system. And asteroids may be the breadcrumbs leading us straight to it. Let's rewind to 2016 when astronomers Konstantin Batygin and Mike Brown at Caltech noticed a peculiar alignment among a group of trans-Neptunian objects, or TNOs, Boise asteroid-like bodies beyond Pluto. These distant objects had elongated orbits, all pointing in a similar direction. Statistically, this shouldn't happen unless some large gravitational influence is guiding them. Their conclusion? A planet about 5 to 10 times the mass of Earth, orbiting between 400 to 800 AU from the Sun. For reference, Neptune orbits at 30 AU. That means Planet 9 would be at least 10 times farther out than the outermost known planets. But here's the kicker. We haven't found it yet. So how do we know it might be there? Because of asteroids. Specifically, detached objects, like Sedna, 2012 VP133, and others with orbits that can't be explained by known gravitational influences. Their perihelia, closest points to the Sun, are so far out it's as if something pulled them into place and then left them there. The orbits are too similar to be coincidence. These icy worldlets seem to be tracing the edge of a gravitational field belonging to something we can't yet see. Some scientists propose alternate explanations, such as a collective gravitational effect of many small bodies or an observational bias. But simulations repeatedly show that adding a massive distant planet explains the clustering perfectly. Well, where is Planet 9 hiding? The challenge is visibility. If it's real, Planet 9 could be thousands of times dimmer than Neptune. It reflects very little sunlight, it moves slowly across the sky, and it's likely located in a region that hasn't been thoroughly surveyed. But we're getting closer. Telescopes like Subaru in Hawaii, Dark Energy Survey, and the upcoming Vera Rubin Observatory are scanning deeper and wider than ever before. These instruments may soon catch a glimpse of the elusive object. And again, asteroids are playing a crucial role. Each new TNO we discover provides another clue, another dot on the map. Their orbits act like compass needles, pointing toward Planet 9's possible location. If found, Planet 9 would redefine our understanding of the solar system. It could be a captured rogue planet, a B super-Earth that never formed close to the Sun, or even the harsh core of a failed gas giant. Its discovery would confirm that our solar system is far stranger and more dynamic than we imagined. And it would explain why the outer solar system is populated with so many tall, scattered, tilted, and oddly behaving asteroids. Some theories even go further. Could Planet 9 have moons, rings, a thin atmosphere? Could it be the reason for long-period comets? Could it affect solar system stability over cosmic timescales? And then there's the fringe. Some speculate that Planet 9 might be Planet X, a long-rumored world tied to ancient myths or modern conspiracy theories. Others have proposed it could be a primordial black hole, the size of a tennis ball, but with Earth's mass. While most of those theories are unlikely, they reflect a deeper truth. We still don't fully understand our own backyard. And that's what makes Planet 9 so exciting. It's a reminder that even after centuries of stargazing, unseen worlds still await discovery. It shows that asteroids, once thought irrelevant, are now guiding us to profound revelations. At Infinity Beyond, we follow the clues, no matter how faint, distant, or cold. Because every asteroid with a strange orbit, every icy body at the edge, every deviation from expectation might be pointing towards something big, something real, something just beyond the dark. So keep watching the sky. Planet 9 may be closer than we think,